I will begin. So we are talking about the area problem. So in particular, we want to describe area bounded by y equals f of x and the x-axis. For a less than or equal to x, less than or equal to b. All right. And I'll assume f is like positive just to get us started here. So basically, like here's a, here's b, all right, and the function. I don't know what it looks like exactly, but just kind of think about an arbitrary function. We'd like to find the area of that region, all right? So here I'll shade it with some inferior chalk. What's this area, right? So how should we figure that out? Like, what's the way to mathematically describe this area? Integral? That's a bad decision. Yes, integral is where we're going, but and we're trying to motivate that, all right? That's our goal today, is to motivate why we define the integral as we do. So how about this? As a starting point, maybe we should think about maybe using rectangles to approximate the area, right? Like we could put this rectangle here, right? And then we could use this one like that, and then this one like this, right? And then this one like this, and then one here like this, and this one like this, and that one like that, right? And then something like that. Now, while I haven't managed to achieve this, I was trying to draw, just for the simplicity of things, I was trying to draw the rectangles so that they have equal width, all right? And what I'm doing here, right, is I'm using the the left endpoint of each of these regions to define the height of the rectangle, right? So this picture I'm drawing would be the so-called left endpoint rule. Let's see here, 1, 2, 3, 4, 5, 6, 7, 8. This would be an illustration of L8, the left endpoint rule with 8 segments, all right? Now, I want to describe to you how to like actually set up the formula for that, all right? So to do that, we need to develop some like standard notation for this lecture, and here's what it's going to be. We're going to say A is equal to x of naught, all right? Then the first point right here is x1, this one's x2, this one's x3, right? And b is going to be xn. So let me just write it out here. x0 equals to a, x1 is equal to a plus delta x, x2 is equal to a plus 2 delta x, and so forth and so on. Xn is equal to a plus n delta x. So what's delta x? Delta x is the width of the boxes we're talking about here, all right? So So like generically speaking, what I'm saying is that the ith endpoint, the ith point is equal to a sub 0 plus I times delta x, all right? And here, what is delta x? Delta x is equal to b minus a divided by n, all right? So if we look at the ith rectangle here, right? So if this right here was the ith rectangle, suppose this one's the ith rectangle, all right? What is the height of it? Well, the left endpoint there is x sub I. Well, that's not true. The first rectangle, what's the left? So here's the first rectangle, right? What's the area of this one? Of the first one, it is f of x naught, right? That's the height, f of x naught times delta x. That's the area. So the ith rectangle, it goes from xi minus 1 to xi, right? So it's based on the subinterval x sub I minus 1 to x sub I. So this is the left endpoint, and this is the right endpoint. So what that means for us is that the left endpoint rule will be the sum I equals 0 to n minus 1 of f of xi delta x. This is how we calculate the left endpoint rule. You can check it out, right? That starts at 0, and it goes all the way to n minus 1. That's the last. So the nth box has the n minus 1th partition point. So this scheme here, this is a partition. I mean, this is partitioning a comma b into n subintervals of equal length. We've partitioned the closed interval from a to b into n subintervals of equal length. So that would be the left endpoint rule. What would the right endpoint rule be? So the right endpoint rule, I haven't drawn the picture of it, right? But it would be based on using x1 to define the height of the first box, right? And then x2, f of x2 would define the height of the second box. F of x3 would define the height of the third box, and so forth, right? So the right endpoint rule, you do sum I equals 1 to n of f of xi delta x. This is the right endpoint rule. Have you guys never seen this summation notation before? Is this your first time seeing this symbol? Seen it before somewhere? Not? Yes? You've seen it? Seen it? But not familiar with it, but seen it? Okay. I'm not saying you have to know it backwards and forwards and upside down. If you read my notes, I define it carefully and prove properties about it and such. I might have relegated those to the appendix. But this is the left endpoint rule. This is the right endpoint rule. Right? So here, let me actually work out an example by hand. So we'll do something relatively simple, something like f of x equals to, how about x squared? All right, that's pretty easy. I'll make it a little bit more complicated, x squared plus 1. All right, and we're going to look at the closed interval a A equals to 1 and B equals to 3, all right? And we'll set up N equals to 4, all right? Let's set up the, L4 and R4, all right? So X naught here equals to 1. What's delta X? I should probably have done that first, right? What's delta X here? Delta X is B minus A over N, right? Which here is 3 minus 1 over 4, 2 over 4. So delta X is 1/2. I'm going to write it as 0.5 here because I find that convenient for numerical calculation. So, okay, so let's get it out here. X sub 0 is A, right? Which in this case is 1. That's given. X1 is 1 plus delta X, right? Which is 1.5. X2 is 1 plus 2 delta X, right? Which is 2. What's another way you could think about this? Another thing that's true is that X sub I plus 1, right, is X sub I plus what? Plus delta X. So this is, this is a key idea. To get to the next sort of, the next point in the partition, you just add delta X because we're taking subintervals of equal width, okay? So X2 is 2, X3 is what? Add 0.5, right? 2.5. And X4 is 3, which of course is B, right? Start at A and go all the way over to B. Does that make sense what we're doing so far? Now, how would we actually calculate L4? L4 is the sum, right? I equals 0 to 3 of, f of xi delta x, right? So if you look at that, first of all, there's a delta x on every term, so you can just factor the delta x out of the sum like that if you like. That's a convenience. Like you're multiplying everything in the sum by delta x, so why not just factor it out? And so what we're looking at then is 1 squared plus 1, that's f of 0, right? Plus 1.5 squared plus 1, that's f of 1. 2 squared plus 1, that's f of 2, and then 2.5 squared plus 1, that's f of 3. And all of that gets multiplied by delta x, which in this case is 0.5. So you have to, take your function and evaluate it, right, at the partition points. Start at A, and I go all the way to 1 less than B. This is the left endpoint rule. And so I can do the arithmetic here. There's 4 1s, so I've got 4 plus 1 plus 2.25 plus 4 plus 6.25, all times 0.5, which I believe is 10, 15, 17.25 divided by 2, which is, it's a mess. It's 8.5, 8.625, I think. I could be wrong about that, but all right, I'm just going to hope I'm right. There's L4. What's R for? I'll write it up here. Sum I equals 1 to 4 of f of xi delta x. Again, I'll factor out the delta x, you know. So I'll write it out symbolically to start with. This is f of x1 plus f of x2 plus f of x3 plus f of x4. Notice the difference, like down here, this one was f of x3, right? And if I can sneak it in, if I can snake my way in here, that was f of x naught, you know? So the difference is with the right endpoint rule, you start at 1 and you go all the way to n. But of course, a lot of the numbers are the same, right? So that's like, you know, x1 was 1.5 squared plus 1 plus 2 squared plus 1 plus 2.5 squared plus 1. What was x4? x4 was 3 plus 3 squared plus 1 all times 0.5. So like the arithmetic here, you got how many ones you got? 1, 2, 3, you got 4 ones. So I got 4 plus 2.25 plus 4 plus 6.25 plus 9 all times 0.5. So that's 13. Well, it's 8 plus 9 is 17. 17 plus 2 is 19. 19.25. 19.25 plus 25. 25.5, I think, divided by 2, so you got 12.75, I think. I could have made a mistake, though. Let me double check there. 15, 19, 21, 25. I think it's right. Okay. So the right endpoint rule is much bigger than the left endpoint rule. Does this make sense for this example? Let's think through it. All right. What does the graph of the function we're looking at here look like? I'll put it here. So we've got, you know, we're going from 2 to 3. Right? And so we're x squared plus 1. So, I mean, I'm going to draw this very approximately, but it's something like this, right? That's a very bad graph of it. It's steeper than that, isn't it? I don't know. I mean, so I'm not drawing the scale the same on the x and the y, obviously, right? So if I made the left endpoint rule in green, it would look something like this, right? If I drew the picture corresponding to the area that we calculated, it's this one, right? So the left endpoint rule is certainly a what? This is an underestimation of the area, right? Underestimate of the area, right? Because as you can see, there's bits that we left out, isn't there? What does the right endpoint rule look like, though? I'll draw that one next to here. I'm never successful in recreating exactly the graph, but you know, the right endpoint rule, and I'll make that one in orange. We're defining the height of each of the rectangles by the right endpoint, right? So it is what? It's definitely an overestimate, right? The true area is somewhere between those two, isn't it? Right? The right endpoint rule, this is definitely an overestimate given the graph, right? Do you agree? So let me ask you guys, can you think of any other schemes we could use to approximate the area? Any other ways we could set this up? Well, one thing I think you talk more about in calculus too, there's also a trapezoid rule. Yeah? So the trapezoid rule basically calculates the area of trapezoids. And it turns out that the trapezoid rule is just the average of the left and the right endpoint rules. So if you take L4 plus R4 and divide by 2, that gives you the trapezoid rule. So the trapezoid rule would be, picture something like this. So the trapezoid rule would be when you calculate the area of trapezoids, because to calculate the area of a trapezoid, you take the average of the heights and divide by 2, multiply by the width, it turns out. That's a formula for the area of the trapezoid. So in short, T4 here, the trapezoid rule with 4 things, would be L4 plus R4 divided by 2, which is what? Let me use my calculator. I'll just say approximately 10.69. All right. But there's another rule. This is actually just for your information only. We don't do trapezoid rule in this course technically. I mean, I might have it in a lab later. I can't remember if I did or not, but it's not something I would test on. Okay. I would test on the left and the right endpoint rules, and there's one other I would test on. The so-called midpoint rule. How do you think we're going to do the midpoint rule? Yeah, okay, very good. Yeah, so like we'll use a new notation, this x bar I. What that's going to be is x sub I minus 1 plus x sub I divided by 2 for I equals to 1, 2, all the way out to n. So the midpoint rule is based on taking midpoints of the intervals we've looked at. Okay, and so the midpoint rule, also known as Mn, is just the sum I equals 1 to n of f of x sub bar I, that's the midpoint, delta x. So that's the midpoint rule. You just define the areas of your rectangles based on the height of the function at the midpoint. Let's calculate this for our example. So M4 for us. So I guess first of all, to calculate M4, we need the midpoints, right? So x1 bar, x2 bar, what are those for us? So the midpoint between, so let me put them in here, it'll be helpful. So this is like 2.5, right? And this is, wait a minute. What? Oh, my pictures are, look, come on guys, don't let me get away with this. Is this 2? That's supposed to be 1, thank you. It's supposed to be 1. So we go 1, we go 1.5, 2 is in the middle, right? Yeah, I can't, it's too small, I can't draw it. So we had 1, we had 1.5, we had 2, we had 2.5, excuse me, we had 3. Goodness gracious, all of a sudden. So the midpoint is here, and here, and here, and here, right? X bar 1, X bar 2, X bar 3, X bar 4, right? And so you can see what that is. Halfway between 1 and 1.5 is 1.25, right? Halfway between 1.5 and 2 is 1.75. Halfway between 2 and 2.5 is 2.25, right? And halfway between 2.5 and 3 is 2.75. And then, so to calculate M4, we can again factor out the delta x, right? And so we have 1.25 squared plus 1, that's f of x bar 1, plus 1.75 squared plus 1, plus 2.25 plus 1, 2.75 plus 1, all times delta x. I hope your eyes are better than mine because I can't see it. All right, so 1.25 squared plus 1.75 squared plus 2.25 squared plus 2.75 squared. So the sum of all the ugly numbers there works out to 17.25. And I've still got 1, 2, 3, 1, so that gets me plus 4 times 0.5. And so what I get is 10.625. And this is pretty typical. The trapezoid rule, all right? The trapezoid rule and the midpoint rule, they tend to be pretty close, right? And they're both more accurate. Typically, they're more accurate than the left or the right endpoint rule. How can we get better and better approximations of the area? What do? We just, rather than using 4 boxes, use 40, right? But do you want to use 40 boxes with a handheld calculator? You do not, right? In your homework, I gave you calculate the left, right, and midpoint rules for 30 boxes. So obviously do not, please, do not use the rest of your week to calculate it with a calculator. Like, that's not the point. We need to learn how to set those kind of things up with like Wolfram Alpha. Like, that's the appropriate way to do it. And you can set up calculations of sums using Wolfram Alpha or other things. But I actually sent you a link to how to literally set up the part B of that problem, which was like, I think, left endpoint rule, or might have been right endpoint rule, with 30 for the function there. The function in that case was sine of x squared. So like sine of x squared, you're going to have to use a calculator for anyway, right? I can't just, what's the sine of 9? I have no idea. I mean, I could calculate it to arbitrary precision, but that's not the point. So do you guys, is this comfortable? Do you see what we're doing? You also see you don't want to do it for large n, right? Now that we've done it for 4, let's talk about what the formula looks like for our example for arbitrary n, right? So I set it up for n equals to 4. Now I want to set it up for just n. Yeah?
One question. Shouldn't it be like over 0.5 instead of 2 there?
Well, multiplication by 0.5 is division by 2. That's fine. See, this is the difference, though, between intermediate algebra and this class. You ask that question, and you feel regret.
Yeah.
There's no regret in the other class. There's no regret. It's just where they are. I mean, a decade of mathematical abuse led to that point, right? But okay, so I need to erase some of this stuff. I'll erase this here. All right, so now I'm going to set up ln, rn, and even mn for our example. Okay? I want to show you how to think through that. We have to think more sort of symbolically, if you will. So we're still working with f of x equals to x squared plus 1, okay? So here's the deal. If delta x is 0.5, right? A is given to us to be 1, and of course b is 3, not that that really figures much into this. So first of all, x sub I is, what is it? We're told it's a plus I delta x, right? So that specifically is what? 1 plus 0.5 times I. That is x sub I. That's a formula for x sub I. Okay? What's the formula for x sub I bar? Well, remember, that's x sub I minus 1 plus x sub I divided by 2. So what's the formula for x sub I bar? Well, it is 1 plus 0.5 times I minus 1, right? Plus 1 plus 0.5 times I. Can we simplify that? I think we can. How's that work out? We got 1 plus 1 is 2. I'll do it here. So we have 2 plus, looks like 0.5i minus 0.5 plus 0.5i. Can we simplify that a little bit? I think we can. So what we have is x bar I. So that's 1.5 divided by 2. 1.5 divided by 2 is 0.75, yeah? 1.5 divided by 2, yeah, 0.75. And of course and we have plus I. So there you go. That's, let me just emphasize here. So we have this, and we have x sub I is 1 plus 0.5i. So I had 2 of them. I added them together. This plus that. It gives me 0.5 plus 0.5, which is 1. Mm-hmm. Now, what's my delta x? I haven't, I actually need to also write that down. Delta x, I said b didn't figure into things. That's not true. It's b minus a over n. That's where b figures in. So that is 3 minus 1 over n, which is 2 over n. Delta x is 2 over n. For us, it was 0.5 because we had n equals to 4 in the numerical work I just finished doing. Yeah? Okay, so now we have everything we need. L4, listen to me, Ln is the sum, right? I equals 0 to n of f of x sub I delta x. And I just need to put in, what is f of x? F of x was given to us to be x squared plus 1, right? So I do calculation sum I equals 0 to n of x sub I squared plus 1. What is x sub I? X sub I is 1 plus 0.5i. I square that, I add 1. That is f of x sub I, right? And then I have to multiply that by what? By delta x, which is 2 over n. That, my friends, is the formula for L sub n for arbitrary n. And you can put that into Wolfram alpha and calculate it for whatever n you like, depending on, well, you know, when I got to 100, it kind of got a little, it only likes to calculate for so long, you know. In contrast, here's Rn. It's pretty much the same, except that the sum goes from 1. Oh, my bad. Was that supposed to go to n? No. It goes to n minus 1 for the left endpoint rule. My bad. Remember, we went from 0 to 3 for L4. Now, Rn goes from 1 to n. And then f of xi, delta x, which in this context is the sum, I equals 1 to n, parentheses 1 plus 0.5i squared plus 1 times 2 over n. So the left and the right endpoint rules look very, very similar. In fact, they share the middle of the calculation is exactly the same, you know. It's just the tail ends which differ. And finally, then there's mn, which actually looks a little bit different for us. Sum I equals 1 to n of, and here it goes, 0.75 plus I squared plus 1 times 2 over n. So I just wanted to give you, an explicit example where I set it up for arbitrary n, so you maybe have a better sense of how to do the homework. You need to kind of like think through the same thing and then implement it using Wolfram alpha, the last problem in the homework, okay? If I can get this computer to come alive, I'll see if we can do one of these here on the... Now, while we're waiting for, so what would the actual area be here? What would you want to do? You want to take the limit as what happens? As the number of approximating rectangles goes to infinity. See, if we did that, then we wouldn't have any error, right? If you could just use infinitely many boxes, you'd have an exact account of the area, right? So that's what we're trying to motivate, this idea that we can take the limit of the number of boxes going to infinity to give us the area. So maybe I should actually write that down. So this is a definition. The integral from a to b of f of x dx is equal to the limit as n goes to infinity of the sum I equals 1 to n of f of x sub I star delta x. Now, here, let me elaborate a little bit more on what I'm saying. So I'm defining what's called the Riemann integral. This is the Riemann integral. Riemann was a 19th century mathematician. Made deep contributions to analysis, another thing. Here, x sub I star is an element of x sub I minus 1 to x sub I, called the sample point. I'll call it the sample point. Not everybody calls that, but I'll just call it sample point. So I'm being vague about that. So you could take the sample point to be the left endpoint. You could take the sample point to be the right endpoint. You could take the sample point to be the midpoint, right? But think about it. What happens as n goes to infinity? Does it make any difference which sample point you choose to define the height of the boxes? Notice that as the boxes get smaller and smaller, the distinction between the heights of these points becomes irrelevant. So in this limit, we expect that it doesn't make a difference which kind of sample point you use. In this limit, they should all come to the same thing, namely the area. All right? So I'm doing a little bit of what's sometimes called hand waving in mathematics right there. I haven't really proved what I just said. In fact, to prove what I just said carefully, you need to study something called measure theory. Measure theory is a more careful account of integration, which makes precise the statements I just said. But for us, this is a good working definition. This is, and we just accept that the x sub I star could be any of them. It doesn't matter. they're all going to give us the same area. It's intuitively clear that they should give the same result, you know? Now the question is, how do you actually calculate such a limit, right? How do you actually calculate such a limit? Can you? I don't know. There's not many of them I can do. Is my computer working? I had to be careful not to cover up the formula, otherwise I'll be in trouble, you know. www.wolframalpha. All right, now, if I was going to be lazier, I would look at, you know, the link I sent you guys in the Blackboard, but I'm just going to try it out. All right, so we want sum from, let's see here, we'll try I equals 0 to I equals n minus 1, oops, minus 1, try that again, of, let's see here, we've got parentheses, 1 plus 0.5i, quantity squared, right, plus 1 times what? Times 2 over n, right? So, see if I can make sure it's in the camera or not. So apparently you can actually calculate these things. Whoa. Yeah, I can't. It's here. I'll make it bigger in a second. So apparently, now these actually are problems I could assign you guys for homework to find these formulas, but I don't because a couple reasons. Number one, it's kind of tedious, but number two, I don't think it's actually indicative of what this course is about. It's within your power to calculate such formulas. It is. All you need to know are like a few basic facts, which are in the notes, which I'll write up on the board here in a second. But anyway, turns out, according to Wolfram Alpha, this is what? Whoa. Oh, I definitely did something wrong. Oh, I'm an idiot. Why'd you guys let me do that? This 0.5s, is this supposed to be 0.5? I was looking at this formula, the formula that I was just looking at. I take the limit as n goes to infinity, I get infinity. Well, that's very bad because the area bounded by this parabola is definitely not infinity, right? It's somewhere around 10, if we're going from 1 to 3. So here's the problem. I put delta x is 0.5 here. How, come on, no, dummy. Delta x is supposed to be 2 over n. 2 over n. My bad. Goodness gracious. So x sub I was supposed to be 1 plus 2i over n. You guys got to, like, stop me before I chase a rabbit this far. Goodness gracious. Oh, stink. And so the x sub I bars are also likewise corrupted. So I'm putting the corrections in green. but that was supposed to be 2 over n. So 2i over n here. 2i over n. Golly. And how about the midpoints? I'll work it out over here. So x bar, I'll work it out in white. Goodness gracious. So x bar I is so let me just fix this. This is incorrect. The problem is I put 0.5 for delta x, but delta x is not 0.5. It is 2 over n for n. You guys let me get away with putting the n equals 4 thing into my general formula. This is not good. Don't let me do that. So we have 1 plus 2 over n times I minus 1 plus 1 plus 2 over n, 2i over n. Or maybe it's helpful to write it as 2 over n times I, because then you can see how to do the algebra. See, I get 1 plus 1, which is 2 over 2, which is 1. And then I get 2i over n and 2i over n, which gives me plus 4i over n. And then I've still got this minus 2 over n term. Ah, it's hurting my thumb. What's wrong with me? All right, so in short, I think this is the simple way to write the formula. X bar I is 1 plus 2 over n times 4i, excuse me, 2 over n times 2i minus 1. I mean, that's one way you could write the formula for x bar I. And then I need to put that down in here. All right. Let me fix then my Wolfram alpha calculation. So I'll give you guys a second. Tell me when you're caught up. See, I knew I did something wrong because when I did the Wolfram alpha calculation, I come up to something that if I take the limit as n goes to infinity, I get infinity, which is an absurdity, right? Because the area is definitely not infinity. It's something around 10. So I knew something was askew here when I saw that, because I can easily see as n goes to infinity, that goes to infinity. So let's see here. We're supposed to not do 0.5. We're supposed to do what? 2i over n, right? Is that right? So I got 1 plus 2i over n squared plus 1. All right, let's see what we get this time. There we go. So what we get, if we trust Wolfram alpha, and I do on this point, is 4 times 8n squared minus 6n plus 1 divided by 3n squared. Now, if you want to do 30, it's easy, right? Just instead of putting n, you put 30 for n, right? I sent you a link with n equal to 30 for your homework, okay? I'm going to make sure it's in the camera. And then I'm going to put the Wolfram alpha away here. Oh, is these bands of rainbow nonsense, unfortunately. Oh well. So I will.
Where's the 2 in the numerator on Wolfram alpha?
The 2 in the numerator.
In front of everything?
Oh, that's because this is 2 over n times that. So let's just put the 2 first. But it is literally this 2 over n, just,
Oh, I got it.
yeah. Wolfram will do that kind of thing. Hey. Okay, so if we trust Wolfram alpha, just suppose we do for a second here. What's the limit? What's the limit of this expression here as n goes to infinity? How would you calculate that limit? Well, we could, how about this? If we divide the top and the bottom by n squared, what we have is 4 times 8 minus 6 over n plus 1 over n squared divided by 3. So what I did was I divided the numerator and the denominator both by n squared. Now it's clear that this goes to 4 times 8 over 3 as n goes to infinity. So what this shows me then, if we believe Wolfram alpha, is that the integral from 1 to 3 of x squared plus 1 dx is apparently equal to 32 over 3. Which is 10.666666666666. Repeating, yeah. That's the exact area. I think we did pretty well with M4. M4 was 10.65. That's not bad for just 4 approximating rectangles. We were pretty close, given the minimum of, the amount of calculation we did, right? Now, the obvious question is, how on earth did Wolfram alpha come up with this formula? What does it know that we don't know about summations? Oh, that always weirds me out. So let me show you what it knows about summations that maybe you don't know yet. Well, there's some really easy things we can all agree on, I think, pretty easily. What do you guys think the sum I equals 1 to n of 1 is? I bet this one you know. I bet this you could figure out. What do you think? I've used k in the notes some. I'll start using k. I could put a k here, It doesn't really matter what you use as the letter. I've been using I up to this point today, but I'm going to use k, if that's okay. Oh, I'm sorry, that's horrible. Anyway, what is this? The next one's not so easy. Yeah? No? No one wants to guess the first one? What happens if you add 1 to itself n times? What do you get? 1 times n, right, which is also known as just n, yeah. Very good. This is less obvious, but it is n times n plus 1 over 2. Gauss knew this formula as a child. So there's a famous story that, his teacher asked him to add, all the children add the numbers from like 1 to 100. And at the time, they had little chalkboards that they wrote on to do math, slates, they're called, And as quick as the teacher asked the question, Gauss wrote the answer on the chalkboard and set it down. It's like, I was trying to buy myself some time to think for myself as a teacher, and the student has plowed through my time waster as if it was nothing, This is Gauss. Because he knew this formula. And there's a way to understand it in terms of like pairing things. But anyway, you can prove this formula. If you want me to show you how it works, try it for 10. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. If we believe the formula, it's 10 times 11 over 2, right? Which is 55. Add these numbers up. 19, 27, 34, 40, 45, 49, 52, 54, 55. What is even less obvious is the following one. Sum k equals 1 to n of k squared. This, it turns out, is n times n plus 1 times 2n plus 1 divided by 6. And there is even a formula for k cubed. I'm sure there's one for k to the 4th as well, which I don't have in my notes, but. So the point is, guys, if you can work out, if you know these formulas, right, then you could go to these kind of expressions and work them out, actually. And that's what's behind Wolfram Alpha's calculation. All right? I don't expect you to do those kind of calculations. I'm just telling you about it for for your information, really. That's it. I want you to be aware of their existence, but that's kind of as far as this goes. I mean, I suppose I could show you an example of it if you want. I'll do something a little bit easier. Suppose we want to calculate the integral from 0 to 2 of x squared dx. Directly from the Riemann definition. We'll use the right endpoint rule because it's easiest. So delta x is 2 minus 0 over n, which is 2 over n, right? And x sub I is 0 plus I delta x, which is just 2i over n, right? And so if we want to calculate the right endpoint rule, we got the sum I equals 1 to n of x sub I squared, right? So 2i over n squared, because that's my f of x, times delta x, which is 2 over n. So there's r sub n here. And all right, so that gives us what? That gives us Rn is equal to the sum, I equals 1 to n, of 2 squared is 4, so I've got an 8 divided by n cubed I squared. But here's the thing. This is a sum over I. N is independent of that. So you can pull the 8 over n cubed out front. So Rn is really 8 over n cubed. The sum I equals 1 to n of I squared. Now that right here